Hello! In today's video, we're going to dive deep into a foundational topic in trigonometry, the graphs of the sine and cosine functions. Our main objective is to construct representations of these functions using the unit circle. This means we'll learn how the oscillating behavior of sine and cosine is directly connected to the motion of a point around a circle. This connection is incredibly powerful and will help you understand the core characteristics of these functions, like their periodic nature and their range. We'll start by revisiting the unit circle and our definitions of sine and cosine. Let's begin with the unit circle. You might remember that a unit circle is simply a circle with a radius of 1, centered at the origin of a coordinate plane. So, we have a radius of 1, and its center is at the point 0, 0. Now, let's place an angle which we'll call theta in standard position. This means its vertex is at the origin, and its initial side lies along the positive x-axis. As you can see, the initial side of our angle theta is on the x-axis. The other side of the angle, the terminal side, will rotate and intersect the circle at some point. Let's call this point P. Here's our point P, which is the intersection of the terminal side and the unit circle. This point P has a pair of coordinates, x and y. A crucial fact from trigonometry is how these coordinates relate to the angle theta. In the unit circle, the x-coordinate of P is defined as the cosine of the angle theta, and the y-coordinate is defined as the sine of the angle theta. This gives us our fundamental definition. For any angle theta, sine is the vertical coordinate of the point on the unit circle, and cosine is the horizontal coordinate. This relationship is the key to understanding their graphs. With that foundation, we can now construct the graph of the sine function. Let's create two coordinate planes. On the left, we'll keep our unit circle, and on the right, we'll plot the function f of theta equals sine of theta. The horizontal axis on our new graph will be the input, theta, and the vertical axis will be the output, which is the sine of theta, or the y-coordinate. Let's trace the movement around the unit circle. We'll start at theta equals 0, or 0 radians. At this point, the terminal ray is horizontal. The point on the circle is 1, 0. Since sine is the y-coordinate, sine of 0 is 0. So we plot the point 0, 0 on our graph. Now, as we rotate the terminal side counterclockwise towards pi over 2 radians, or 90 degrees, look at the y-coordinate of our point P. It starts at 0 and increases. By the time we reach pi over 2, the point is at the top of the circle, 0, 1. Here, the y-coordinate is 1, so sine of pi over 2 is 1. On our graph, we plot the point pi over 2, 1. Let's continue to rotate the ray towards pi radians, or 180 degrees. As we move into the second quadrant, the y-coordinate starts to decrease. By the time we reach pi, the point is on the left side of the circle at -1, 0. The y-coordinate is back to 0, so sine of pi is 0. We plot pi, 0. Next, we rotate to 3 pi over 2 radians, or 270 degrees. In the third quadrant, the y-coordinate continues to decrease, becoming negative. At 3 pi over 2, the point is at the bottom of the circle, 0, -1. The y-coordinate is -1, so sine of 3 pi over 2 is -1. We plot 3 pi over 2, -1. Finally, we return to our starting point at 2 pi radians, or 360 degrees. The y-coordinate increases from -1 back to 0. At 2 pi, we are back at the point 1, 0, and the y-coordinate is 0. We plot 2 pi, 0. Connecting these points with a smooth curve gives us the shape of one complete cycle of the sine wave. Notice that this wave oscillates smoothly between a maximum value of 1 and a minimum value of -1. Now, let's explore the graph of the cosine function. We'll use the same process, but this time we'll focus on the x-coordinate, because the cosine of an angle is the x-coordinate of the point on the unit circle. So, we'll plot the function f of theta equals cosine of theta. The horizontal axis is theta, and the vertical axis is now the cosine of theta, or the x-coordinate. Again, we'll start at theta equals 0. At this point, the terminal ray is horizontal. The point on the circle is 1, 0. Cosine is the x-coordinate, so cosine of 0 is 1. We plot the point 0, 1 on our new graph. Now, let's rotate to pi over 2. As we move towards the top of the circle, notice that the x-coordinate of our point P decreases from 1 towards 0. At pi over 2, the point is at 0, 1, and the x-coordinate is 0. So cosine of pi over 2 is 0. Let's continue to rotate to pi. As we move into the second quadrant, the x-coordinate continues to decrease, becoming negative. By the time we reach pi, the point is at -1, 0. The x-coordinate is -1, so cosine of pi is -1. We plot pi -1. Next, we rotate to 3 pi over 2. In the third quadrant, the x-coordinate starts to increase from -1 towards 0. At 3 pi over 2, the point is at 0 -1, and the x-coordinate is back to 0. So cosine of 3 pi over 2 is 0. We plot 3 pi over 2. Finally, we return to our starting point at 2 pi. The x-coordinate continues to increase back to its starting value of 1. At 2 pi, we are back at the point 1, 0, and the x-coordinate is 1. We plot 2 pi 1. Connecting these points with a smooth curve gives us one complete cycle of the cosine wave. Just like sine, the cosine wave oscillates between a maximum of 1 and a minimum of -1. Let's summarize the key characteristics of both the sine and cosine functions that we've just uncovered. First, the domain of both functions is all real numbers. This makes sense because you can rotate around a unit circle any number of times, in either direction. The input, theta, can be any real value. Second, the range of both functions is the closed interval from -1 to 1. This is because the y and x coordinates of any point on a unit circle must be between -1 and 1, inclusive. Third, both functions are periodic. After a full rotation of 2 pi radians, the coordinates repeat. This means the graphs will repeat their shape over and over. The period is 2 pi. A very important observation is how closely related these two graphs are. Let's look at them side by side. Notice that the graph of cosine looks exactly like the graph of sine but shifted to the left by pi over 2. In other words, if you take the sine wave and move it pi over 2 units to the left, it lands perfectly on the cosine wave. This relationship is formalized by the identity. Cosine of theta equals sine of theta plus pi over 2. This shows that the cosine function is simply a phase shift of the sine function. They are fundamentally the same wave, just starting at a different point. Let's work through an example to solidify our understanding. Suppose we need to identify the function from a graph. We're given a sinusoidal wave and need to determine if it's a sine function, a cosine function, or something else entirely. Here is our graph. It clearly has the shape of a sine or cosine wave. To identify it, we need to focus on two things: the starting point and the direction of the first movement. First, let's look at the starting point, the y-intercept. This is where the graph crosses the vertical axis. We can see that when x equals 0, the y value is 1. This is the graph's maximum value. This is the signature start of a cosine wave. Let's compare this to what we know. A standard sine wave starts at the origin, 0, 0, and goes up. A standard cosine wave starts at its maximum, 0, 1, and goes down. Our graph matches the cosine function. So, just from the starting point, we can conclude this is a cosine wave. A second check is to see if it moves in the correct direction. From its starting point at 0, 1, our graph moves downwards. This is consistent with the cosine function, which decreases immediately after x equals sine 0, as its x-coordinate moves from 1 towards 0. The graph starts at its peak and immediately begins to fall. This is another confirmation that we are looking at a cosine function. So, by observing the start and immediate direction of the graph, we can confidently identify it as a cosine wave. This skill of describing function characteristics from a graph is an important one. Let's work through one more example to reinforce these ideas. This time, let's say we are asked to sketch the graph of f of x equals sine of x. We need to construct this graph by plotting points. Let's use the key angles we found from the unit circle. We'll set up a table of values for x and their corresponding sine of x values for one full period, from 0 to 2 pi. We'll include the quadrantal angles 0, pi over 2, pi, 3 pi over 2, and 2 pi. From our previous construction, we know these values. At x equals 0, sine is 0. At pi over 2, sine is 1. At pi, sine is 0. At 3 pi over 2, sine is -1. And at 2 pi, sine is 0 again. Remember, sine represents the y-coordinate of the point on the unit circle. Now we can plot these 5 key points on a Cartesian plane. We'll label our x-axis with radians and our y-axis from -1 to 1. First, we plot the point 0, 0, then pi over 2, 1. Next, pi over 2, then 3 pi over 2, minus 1. And finally, 2 pi, 0. The last step is to connect these points with a smooth, oscillating curve. It should start at the origin, rise to its maximum, fall back to 0, descend to its minimum, and return to 0 at 2 pi. Since the function is periodic, to sketch a longer graph, you would just repeat this 2 pi long cycle over and over again to the left and to the right. And that's how you construct the graph of the sine function from its fundamental points. So, let's quickly recap what we've covered today. Our objective was to construct representations of the sine and cosine functions using the unit circle, and I hope you can now see the intimate connection between the two. We learned that on the unit circle, the y-coordinate gives you the sine of the angle, and the x-coordinate gives you the cosine. This definition is the foundation for understanding these periodic functions. We constructed the graphs by tracking these coordinates as we rotated around the circle. This showed us that both graphs oscillate between -1 and 1 with a period of 2 pi. Remember, the maximum value is 1, the minimum is -1, and both functions repeat every 2 pi radians. We also observed the critical phase shift relationship, where the cosine graph is just the sine graph shifted left by pi over 2. And we practiced using key points like the start and immediate direction to sketch and identify these graphs. Understanding this unit circle connection is key to mastering sine and cosine. It's a powerful visual tool that explains their behavior. Thank you for watching.